So even though, and this is going to kind of begin our discussion of finite elements, okay? Because even though we to some extent have introduced a systematic way of coming up with, or utilizing Ritz method, but really the only thing we said was, okay, we're going to use polynomials for for better or worse, unless we know some other, unless we know something else about the solution a priori. We're just going to use polynomials, and we'll just take more and more terms until we converge to the exact solution, right? And then the other thing is that those, the interpolating functions, or the approximation of the functions, they just need to satisfy the essential boundary conditions, okay? But the problem is, especially when you go to 2D, I mean, in 1D, as long as your solution is smooth, and in other words, it doesn't have a discontinuity, in 1D, it's almost always okay to just assume that the solution is some polynomial, right? I might have to take 100 terms, right? If you had a really heterogeneous material properties, like say, E of x was some real crazy function of x, something like that. Well, then your solution's also going to be crazy. But if I take enough terms of the polynomial, it's I could fit this curve, right? And to some extent, even if it was discontinuous, if I have enough terms, I could get close, right? If I have enough terms in my polynomial. But when you go to 2D or 3D, where you actually have some structure, it's very, very difficult, if not impossible, to figure some polynomial that can approximate the solution over something that looks like that, right? But if we break this thing up, then we sort of just have two bars, right? Two one-dimensional things, right? One here and one there that we kind of know. Now, I'm not really saying these are bars. In a bar, you'd only have axial motion, right? Here it's, potentially you could have transverse motion as well, right? But nevertheless, I mean, we can, if we break these up, then we can come up with some polynomial interpolant too that does a pretty good job over the field of interest, okay? So also, when we break it up into small, simple shapes, we can truly introduce a systematic way of determining what the interpolating function should be, okay? So we're working in 1D right now, so we're going to have a domain, okay? So here's the total domain. And we're going to break this thing up into two pieces. So we're going to break it up into two domains, two subdomains. So this is the domain of element 1, and this is the domain of element 2. Of course, we're going to call them elements, right? And we're going to give these the intersections of the elements. We're going to call them nodes, and we're going to number them. So we have, that's node 0, node 1, node 2. All right? And the position of node 1 we'll call XA. The position of node 2 we'll call XB. And we're going to pull out element 2 and look at it in isolation. Right? So we're going to pull it out. So this is element 2. Sometimes we'll number the elements, and I'll try to use a circle around the element number. So this is element 2, and it has nodes 1 and 2. And let's assume a linear field over that element. Right? So we're going to assume the solution is linear. Therefore, it's going to have a construct like that. And let's evaluate what the displacement is, or the field, okay? And so I just want to make a lot of times, we just use a generic variable u, okay? And since I haven't introduced any physics, we're just talking about u as a field variable, meaning if I'm solving elasticity, it would be displacement. If I'm solving heat diffusion, it would be temperature. If I'm solving the diffusivity equation, it would be pressure, right? So it's just some generic field that we want to solve for, okay? And we're going to assume that the field over that element has a linear form. And so let's evaluate the field at the nodes, right? So at node 1, the position is XA. So then we have C1 plus C2 XA. And we're going to define that as U1 E2, right? So the field variable at the first node of element 2. And likewise, we can evaluate this at node 2. So node 2 has position XB. So maybe just to be clear, this is at node 1. This is at node 2. So at node 2, we have XB, C1 plus C2 XB, and that's defined as U2 E2. Okay? So I'm just going to rewrite these equations, particularly these equations, in matrix form. Right? So I have U1 E2 U2 is equal to 1 XA, 1 XB, C1, C2. All right? So then in matrix notation, or vector notation, I might call this UE2, the vector UE2 is equal to, I'll call this A, I'll call this C. All right. So what's the solution? If I want to solve this for C, what's the solution? Yeah. C equals A inverse U. Okay. So if we were to actually compute the inverse, then we'd get C is equal to so that's a vector. So the first term is C1, second term is C2. All right. So if we go back and we write, we had U equals C1 plus C2, right? So if we C2x, right? So if we write this in terms of these guys, then we have, maybe I'll go to the next page just to leave myself room. So we have So we have that. So if you remember, in the finite element method, we said we want to seek a solution U of H that's the sum of some unknown coefficients Uj times a shape function. And I think maybe I used psi or phi. I'm going to start using n. I'm going to try to use n for the, n will be the shape functions or basis functions for the rest of the class. I'll try to be consistent. Okay. And so if we write that as, write it out for this element where we have two unknown coefficients, it's U1, E2, N1 plus U2, E2, N2. So if we rearrange the first equation to look like the second, so we want to rearrange the first equation so that you have some function of x multiplied by U1, some function of x multiplied by U2. Okay. So we just rearrange the first equation in that form. What we get is we get that. So therefore this is N1, this is N2. And if we let xb minus xa equal to L, then you'd get this guy. And we can write this in matrix form like this. And in that case, this is going to be a shape function matrix or vector. So that's these are for linear, an assumed linear field. This is your shape functions and times your unknown coefficients. So the total solution, U of H, is equal to the shape functions times the unknown coefficients, right? And in just a second, it'll be, I mean, we took a lot of sort of steps, but in just a second, you'll see that it's a very, very clear, simple, systematic way to determine what these are. Even though what we did was just manipulate some equations. We didn't do anything really fancy there, just some algebra. But the algebra would get pretty wieldy as we go third order, fourth order, fifth order, right? So let's look at quadratics.